Thanks. I'm really grateful to the organizers for letting me speak in spite of not being able to be there, because this is for me a fantastic opportunity to hopefully get some feedback from real experts about what we think is an interesting percolation type phenomenon that we've kind of come across by accident in our work. And when I say our work, all the work was basically done by Shaunak Biswas, Ritesh Bola, Muslin Islam, and some of it later by Shaubik Kundu and Saeed Ansari. All of them were at some point or the other students in TIFR Mumbai and worked on this during their thesis and soon after. Um, so let me just start. I'm going to have a few slides where I talk like a physicist and just use physics jargon. And I've tried to mark those slides with some redundant physics or physicist type words in the title. So in these slides, if there's stuff you don't fully follow, that's fine. It's just to give you a flavor of why we are interested in these things. And then when we talk about what we actually did, hopefully everything will be uh, reasonably precise. Maybe not as precise as math talks usually are, but I'll do my best. Uh, so the starting point for us, when we think about a crystal of metal, for example, is that electrons behave like waves and they behave like particles. That's the famous wave-particle duality of quantum mechanics. But if you're in a good metal, it's good to think of them as waves. And then what you have to do is just find the eigenmodes of this wave equation, which is the Schrodinger equation. That's governed by the form of the crystal potential. And then once you find these modes, each mode frequency is up to some prefactor, the energy of the allowed state of the electron. And then Fermi and Pauli together tell us that we should fill them up one by one from the bottom up in increasing energy until we've got all the electrons we want in the crystal. And in this way, we get to some energy level, epsilon, Fermi, the Fermi level. And most of the physics we are interested in at low temperature has to do with the properties of these eigenfunctions of this linear Schrodinger operator at this energy. And then, of course, there's complications having to do with the fact that these actually are charged particles that interact. But for what I'm trying to say here, that's largely it. What is, though, quite relevant for us is that this description is only true of a sort of perfect crystal where you have this perfect periodic potential. And in any real life sample anybody makes, there's always missing atoms or extra atoms or some lattice imperfections. And these imperfections are static, though they don't change on the time scale of any experiment. So in physics jargon, we think of it as quenched disorder, quenched in the sense that it's some random potential that is fixed once and for all, and it takes on a particular value or a particular shape, random shape in one sample, which will be different from another sample, and then you have this ensemble of samples, which is an ensemble of random potentials. And this is quite a common thing to happen in condensed matter systems. People work very hard to make things pure, but in the end, there's always some disorder. And it's this disorder that we are focusing. If the disorder is weak, it can actually serve as a probe of what's going on inside in the pure system itself, because it brings to the fore some correlations in the pure state. For example, if you have some extra atom in a material, around the extra atom, you can go in and measure the spin texture, and that tells you something about what was going on before you put in the extra atom. And if the disorder is very strong, it can lead to entirely new phases of matter. Some of these you may have come across in a mathematical context, for example, spin glasses. And that's why we are interested in the end, topics like percolation. So we will come to that in a minute. And when we think about these sorts of disordered systems, there's a kind of a dogma among physicists, which kind of goes as follows. Um, so I'm always talking in the large size limit, in the limit that the sample size goes to infinity. In physics, we call this infinite volume limit the thermodynamic limit. So I'll use that phrase interchangeably. The strong version of this dogma is that properties are self-averaging in this limit. Physical properties of the type I'm usually interested in and I can measure are sums of local quantities over the whole sample. And these tend to be self-averaging, and in the sense that sample-to-sample fluctuations are small, or the average across all samples you make with the same sample preparation protocol matches the typical value of the noise. We know that violations exist. There are systems that we have studied in condensed matter physics where the average and the typical values across this ensemble of samples can be different. And in the jargon, these are characterized by what are called infinite disorder fixed points. That's just jargon. Uh, so we know that this can sometimes not happen. This cannot work. But there's a weaker version of this dogma, which we tend to really believe in, and we don't know really any well developed or well understood examples where it's violated. And this weaker version says that at a minimum, if I make two samples with the same sample preparation protocol, which means drawn from the same ensemble of random samples, then at low temperatures, their qualitative behavior must be the same at a qualitative level. So the numbers you measure might be different, but the qualitative properties will be the same. And by qualitative properties, we mean something reasonably precise in physics terms, at least. We mean that they must be in the same phase of matter, the same thermodynamic phase of matter. If you want to think in terms of probability distributions, what this weaker version really says is that even if the probability distribution of some physically measured quantity, probability distribution in this ensemble of samples, even if this distribution is broad, it's still a single sort of peak. Can be a broad peak, but it's one peak. It's not two well-separated narrow peaks. Two well-separated narrow peaks would kind of mean that there's two kinds of samples. One of them behaves in one way, one behaves in another way. And then they would not be in the same phase in the way we think about phases in thermodynamics. So that's kind of the weaker version of the central dogma. And the reason I'm bringing this up is we seem to have stumbled across an example where even this weaker version seems to be violated in the percolated phase of some system. And that's what I want to tell you about and hope to get some feedback from you. So let me now just define the language that we are used to using when we talk about percolation. So for us, percolation is motivated by the idea that if you want to think of transport of a classical fluid in a porous medium, it's really the random geometry of the medium that largely determines whether the fluid can go from one place to the other. And so the natural thing to then study is the end-to-end connectivity of a porous medium. Can you go from one end to the other? And the simplest model, as all of you know, of course, is a randomly diluted regular lattice, like you take a square grid or a triangular grid or a cubic grid, and you just randomly remove vertices. And for me, L is always going to be the linear size of the entire sample. So if it's a square grid, it's L by L or some aspect ratio L time and alpha L. And if it's a cubic thing, it's L by L, like that. And NV is always going to be the density or fraction of sides, vertices that I remove randomly. Right? It's the dilution fraction. And T of L and NV is simply the probability of answering yes to the question, can I go from one end to the other? Along the existing sides and bonds, along the existing edges and vertices of this graph. Now I'm going to be a little sloppy about whether I'm talking about literally the crossing probability with open boundary conditions, or I'm going to put periodic boundary conditions and make it a torus. And then I'm going to talk about wrapping probabilities. Can I go around? And if I'm talking about latter, I will sometimes want to know whether there's a cluster that can wrap around in more than one independent direction, let's say in 3 dimensions, or not. So we'll come to that. But basically, P is a quantity of this type. It's a crossing probability. And for us, the most basic question is, how does this behave as a function of NV and L? And that's what percolation theory tells us. It tells us that there's a threshold behavior to this, and it goes to 1 in the large L in the thermodynamic limit for small dilution, and it goes to 0 for large dilution. And from the physics point of view, the most remarkable thing about this is that near the critical point, near the phase transition, near the threshold, there's critical behavior which is universal, by which we simply mean that this function of two variables collapses onto a function of a single scaling variable constructed like this. where nu is the scaling exponent, the correlation length exponent that we define. And this depends only on the dimension. In 3 dimensions, we believe all 3-dimensional lattices will have the same function f and the same exponent nu. In 2 dimensions, we again expect the same thing. All planar graphs will have the same function f, different from the 3-dimensional one, of course, and a different exponent nu, but will be common to all the 2-dimensional cases. And this is an example of scale invariance of the type that we believe crops up again and again at all second-order thermodynamic phase transitions. Most of these other phase transitions are very complicated, don't have a simple geometric picture. So what's fascinating from a physics point of view is that here you have a completely geometrical example of this more general phenomenon that we are used to thinking about and trying to understand. So for us, it's the simplest example of a thermodynamic phase transition. And just to peek ahead, what I'm going to hopefully convince you of is that we have a phase transition of this type, a percolation transition, in maximum density dimer package, which I will define, of weakly diluted lattices. And in the percolated phase, we have this violation of even this weak form of what I'm calling the central dogma. And you'll see that the reason for this, the underlying reason for it is somehow that there's very long range correlations in what the ensemble of the disorder is. So that's sort of my setup. And thus far, I've been kind of vague, not really said things precisely. So now let me try to get a bit more precise. But at this point, are there questions about my jargon or terminology or anything like that? Please do ask. It's a bit difficult to gauge on Zoom whether I'm losing the audience or not. So I'll just pause for a minute to just find out if there's any questions about the language. No? Okay. So let me proceed.
There's one question.
Yeah, sure.
Hello.
Yeah.
Does this root cause, or maybe the phenomenon that is highlighted in purple, does this cause the appearance of Griffith singularities in the model? So points at which the free energy or thermodynamical quantity would be non-analytic, but you're away from the critical point.
I see what you're asking. You're asking, is there a extended regime in parameter space where I'm what I would call critical? No, that's actually not the strange thing that's going to happen here. We are going to get a perfectly honest percolated phase, nothing critical about it. But roughly speaking, just to peek ahead in the spirit of this slide, what's going to happen is if I have this ensemble of identically prepared samples, disorder realizations drawn from the same ensemble, roughly half of them will have clusters of a certain type percolating and the other half won't. So if you wish, it's going to be a percolation transition where this function doesn't go to 1, it goes to something like half or some number throughout the percolated.
I was referring to the annealed model, so the model in which you average over the randomness of the defects.
Yes, so, but my defects, so of course I'm averaging over the defects in the sense that I have an ensemble of samples, which I make by introducing the disorder. So I have, let's say, 1 million such samples, all obtained by randomly diluting 5% of the vertices of this graph, right? And then I don't know what you mean by average over the disorder, but I'm just going to ask this yes/no question each time, and the fraction of times I get yes is this P, right? And I'm saying that typically we expect P to go to 1, but here, roughly speaking, it's going to go to half throughout the. And that's other strange things that will happen. That's what I mean by violation of this central dogma. Because for me, when P goes to 1, that's sensible. It says that all the samples are in the percolated phase. If I'm thinking of a metal, all of them will conduct. If P is 0 in the thermodynamic limit, then nothing will conduct. They're all insulators. But if it's half, then half the samples will behave in one qualitatively different way from the other. That's what I mean. The question you're asking about Griffith's phases is interesting and does crop up, for example, in these examples. When we look at certain quantum mechanical Hamiltonians defined in terms of spin operators, with random couplings, then there can be an extended range of parameter space where the behavior, the free energy is singular. So that does happen in these examples. And the average value throughout is not equal to the typical value. The distributions are very broad. So there's a tail going to zero of various quantities. But that's not what we are going to be finding. We are going to find this something that's at the same time simpler and more dramatic.
Thank you.
Does that at least answer half your question? Or did I misunderstand the question?
Yes, thank you.
Okay, all right. So now let me start getting a bit more specific. When we think of percolation, we're just thinking of a classical fluid going through. But when I look at these electron waves in the same medium, they can remain localized, not manage to go from one end to the other, even when a classical fluid can percolate through. And that's because you're asking a different question. You're asking a question about the eigenfunctions of this Schrodinger operator. And we know that there are many variants of this phenomenon where they get localized. And in the physics jargon, that's called Anderson localization, after Anderson, who first realized this. I just wanted to mention that to get to sort of the main context of what we are going to talk about, which is the physics of quantum percolation. So now what I'm going to do is I'm going to imagine I have one of these disordered lattices where I randomly removed vertices. And the vertices represent positions of ions. And the electrons can hop from one ion to the next. And if I've removed a site, of course, an electron can't hop there. So this is going to model some class of alloys, alloy systems and metals that were studied in the 70s. And the basic question we are going to ask is this question of Anderson localization. Do the eigenstates of this Schrodinger equation remain localized, or are there eigenstates that extend across the sample, which would allow, let's say, current or heat current to go from one end to allow it to remain a metal as opposed to become an insulator? So we are really asking, is there a quantum percolation transition inside the classical percolated phase? So the geometry is percolated. There is a path to go from one end to the other, but your electron may still not be able to hop in the sense that the relevant eigenfunctions are localized. So there's no eigenfunction that has support both at the left end and the right end of a very large sample. And if that does not happen, then there is no way for heat or electricity to be conducted. So that's the question that was motivated by these alloys in the 70s. And the simplest example of this question, which we will focus on, and we'll only look at simple examples like this. And from this point on, I'll try to be very specific. So I have a honeycomb lattice, so a honeycomb net, which is a bipartite lattice. Vertices come in two groups, A and B, where the neighbors of A are always B and vice versa. And I'm randomly diluting a fraction NB of the vertices. And this symbol refers to the edges that remain, that survive after I've removed randomly this fraction of vertices. They're the edges of the diluted. And RR prime are the surviving sides. And this number T RR prime is random from one edge to the other. It's some complex number. And it's the quantum mechanical hopping amplitude for the electron to go from one place to the next, to a neighbor. And the math problem we're interested in to sort of think about this quantum percolation is simply the spectrum of this Hermitian adjacency matrix of this graph. Adjacency matrix, but weighted. So the entries are TRR prime. For an edge RR prime, the entry is TRR prime. So you get this Hermitian matrix, and we are asking about the spectrum of this. That's the problem. Simple linear algebra problem in the limit of a very large, in the L going to infinity.
Can I ask, are you interested in the spectrum with the dilution quenched?
Yes, the dilution is always quenched. Okay. So what I'm going to do is get the spectrum for a given realization, look at some property of it, then get the spectrum for another realization, look at some property of it. And that's physical for me because these dilutions represent the disorder which is not moving on the time scale of the experiment. So the idea is to do the calculation, whatever it is, for one sample, and then look at the distribution of the answer. In that sense, it's quenched, not annulled. Is that what you were asking?
Yes. Yeah.
Okay. And so when we looked at this in the context of graphene, which can be modeled by graphene with defects, the simplest model for graphene with defects is exactly what I just had on the previous slide. And when we looked at it 10 years ago, we were surprised, and we shouldn't have been surprised as you'll see, but we were surprised at that point to find a non-zero density, which I'm going to call W throughout the talk, of states at zero energy of this Hamiltonian. So now just a couple of words about this matrix. It's a bipartite adjacency matrix. And because it's a bipartite adjacency matrix and it's Hermitian, it's very easy to see that any state at a non-zero eigenvalue epsilon, my eigenvalues, I will call them energies because that's what they are for me. So any state at a non-zero energy epsilon will also have a partner at minus epsilon. And you get the partner simply by taking the eigenvector and changing the signs of all the components of the eigenvector at one sublattice, but not the other. So states come in pairs, epsilon and minus epsilon. And of course, zero is special as a result. And zero energy corresponds to the Fermi energy. Remember this picture where you let the electrons occupy the available states one by one until you fill up how many ever particles you have. So in the case of graphene, the zero of the energy is the energy you would reach if you had exactly one particle per site, which is called half filling because actually there's two polarizations of spin. So one particle per site actually corresponds to half. So this is the half-filled graphene problem in physics jargon. And zero is the energy we are interested in. Physical properties are determined by what happens to the eigenstates at zero eigenvalue. And what we found is that there's a surprising to us at that time non-zero density of zero energy states, null vectors, zero modes. And these were interesting for a different reason that I don't want to get into here. But we looked numerically and we found that there's this density that survives the thermodynamic limit. And we were initially puzzled, but then we had a conjecture for its mechanism, for what produces these exact zeros. And the idea was just a simple sort of linear algebra thing. So we imagined that there is some local sublattice imbalance in this bipartite lattice. So you're randomly removing A and B sublattice vertices completely at random, right? With the probability NB at each side. So globally, you can put in a constraint that says the total number of surviving A-type sites equals the total number of surviving B-type sites. So that's a global constraint. You can put it in by hand. That's not a problem. But even if you did that, there's no way you have of controlling what's the relative density of A and B sites locally, right? Locally, there will be fluctuations. In some regions of the graph, number of A sites will be bigger than B and vice versa. That can happen. Now, typically when that happens, the excess will be on the boundary. But we imagine or conjecture that maybe there are these rare regions in the graph where although the boundary, the site boundary, the vertex boundary of the region, which means all the vertices that talk to the rest of the graph, the vertex boundary of the region is all, let's say, one sublattice B here. And in spite of that being all B, the number of A sites is still bigger than the number of B sites. And there's this imbalance. So the imbalance goes the wrong way in these rare regions. And you can have rare RA type regions or RB. In the B, the role of A and B is just reversed. Now, if you have such a region in the graph, then it's very easy to see that you will get exactly these many null vectors that will live only on the A sublattice sites inside this region, for example. And the argument is simply constraint counting. You write down the relevant eigenvalue equation or set of equations, and the number of independent equations is NB. And you then look for a solution which is non-zero only on all the A sites in this region, and there's NA of them. And you can always find such a solution because the number of constraints is less than the number of degrees of freedom, and you have exactly these many robust zero modes. And in the physics jargon, we call them topologically protected. I think topology means something far more subtle, maybe to mathematicians, but we simply mean the following. If you have a graph, what is connected to what is the topology of a graph, and by how much is it connected? The strength of the graph, this T, this number T, is somehow a decay. So if something depends on whether R and R prime are neighbors or not, but doesn't depend on the value of T, in the physics jargon, you would call it topology. So we found these modes, and realized that they're topologically protected. We found them for arbitrary values of this TRR. They were always there at roughly the same number. And our idea was that it may be coming from these rare regions. So this rare region construction is kind of central to what I have to say. So is this part clear? This is just rank nullity. I've got a rectangular matrix if I just look at this region. That's all I'm saying.
Excuse me?
Yeah.
Simulations you showed were done with which T?
Sorry?
The
Say that again.
simulations in the previous transparency, they were done with which T?
So they were done with a value of TR prime that was centered at unity and with some distribution. And we checked that it didn't matter. That was the point. So you can pick each TRR prime to be an independent random number centered at 1. And the point was we got more or less the same density of states in the larger limit, whether or not, for different realizations. So it didn't seem to matter that it's disordered, that these numbers are not all 1. And I'm emphasizing this point because, of course, you can construct trivial examples of zero modes, which rely on the fact that all the hoppings, all the T's are 1 or the same number. So, for example, here, just to be very concrete, so these circles are vacancies, and I've drawn the honeycomb net now as a brick wall lattice. So you can see that this is basically the same as the honeycomb net. I've just deformed it to make it look like a brick wall. So the circles are the missing sides. So you can see if I have 1, 2, 3, and 4 vacancies, missing sides, arranged in a pattern like this, which can happen with some non-zero probability, if I'm diluting randomly, then if all the T's are 1 or a fixed number, then you can construct a wave function that lives exactly inside and that has zero energy, just by hand, by inspection. But this is fine-tuned. The minute you allow the T to have some jitter, some randomness, this mode doesn't exist. It's not a solution. But here's another example, which is more along the lines of what I was conjecturing here, right? So if I have 6 such vacancies that cluster here, like this, in this pattern, then you can do the counting and you will find there's exactly 1 equation less than the number of variables at my disposal. So I've marked the value of the wave function at all the points on which it's non-zero here. And you can ask how many Schrodinger equations does this have to satisfy? And that count is smaller by 1. So there's always going to be 1 such mode living inside this region, no matter what choices you make for TRR prime locally. So in this sense, this is a disorder robust or a protected mode, and this is not. This is unlikely to be of any consequence, and this is the one that probably matters. That was right. So the key sort of question that remained unanswered by this 10-year-old work was that these were all hand-drawn examples.
Sorry, Kedar. Yeah. I think I'm slightly confused about the model. So can I think as a toy model of what I just want to translate it in my head? So can I think of just taking the adjacency matrix of a supercritical cluster, or is it a different?
So take the picture on the screen. Take the picture on the screen. All the lines are the edges that exist, except for the lines that connect these circles. The circles are not there. They're diluted out. They're deleted. So these 3 lines don't exist. So that's the graph. And now for each line, pick an independent random variable T and construct the summation matrix. That's the matrix I'm talking about.
So basically, you do a site percolation.
Yes.
And then you with the resulting graph, you have a weighted graph.
Exactly. Exactly.
But if you don't have, and maybe this is what you were saying. So if you don't look at the weighted graph, but you just look at the site percolation.
Yes. If you did that, you will also get a contribution from these kinds of modes, right? Which are special, which only exist because all the weights are fine-tuned to be equal. And so this is what I meant when I said, when we check this number, the value of the zero energy density of states, the weight of the delta function at 0, that number was more or less the same whether or not we introduced the randomness in the T or not. And the more or less has to do with the fact that there's a small contribution coming from modes like this that only exists when I don't have any disorder in the weights.
Right.
The dominant thing is from things like this, which exists no matter what weight you put. That's the point. That's why, in the physics jargon, we call them topologically protected. They're protected against this disorder. These ones are fine.
Can I just see the simulation again, just to digest it? I didn't.
So this is the number of modes divided by L square. It's a L by L sample, well, 2L square actually, because it's 2L square sites for a L by L sample in my notation. And this is the thermodynamic limit I'm claiming. So it's a decreasing function of the dilution, but it's not going to zero. And the reason I'm claiming I know the thermodynamic limit is I can measure this density as a function of 1 over L and go to a regime where L is large enough that I get these flat lines that I can extrapolate to the origin in the 1 over L axis. So when I extrapolate this line all the way here, that's the number I mark on this graph.
Sorry, the NV is
dilution, is the fraction of missing vertices. And for me, NV is always the fraction of missing vertices, and W is the density. There is a number of zero modes per unit site.
Okay.
So these are both densities. And I'm claiming I can estimate the limit, the L going to infinity limit W like this, numerically. That's the numerical experiment we had done 10 years ago. The fact that this is a flat horizontal line allows me to say that I know what the limit is. That was the idea. It's an experiment.
Okay, thanks.
Right? And the point is that that answer didn't change whether or not we put some jitter in the T's. And we believe that was because the dominant effect was from these robust modes. That was the idea 10 years ago. But it left this question unanswered. What actually determines this dominant answer? How do you find these rare regions? We can construct some examples like this one, but they are terribly low in probability. You need the 6 things to come together in a certain pattern. The probability for that is really tiny at, let's say, 10% dilution. So that's not what's causing what we see. What we see is much bigger. And we check that these are not a floating point artifact by going and doing some fairly complicated numerical checks. So there's a genuine puzzle here. What dominates this zero energy density? That was the question. And our first clue as to what to do was that somehow it's coming from local sublattice imbalance, as I emphasized. And dimers provide a way of enforcing sublattice balance on a bipartite lattice at the shortest distance scale you have on the lattice, one edge, right? And so the idea was maybe we should start thinking in terms of dimer covers, which in computer science language are called matchings. And the idea very crudely for us was that regions of the lattice that cannot be perfectly covered by dimers host these wave functions. And there's some history to this, which I'll come to. It's not entirely, it didn't come out of the blue for us. There was some history we had read about. So I'll tell you about that. But this was the idea. So let me just have one slide language primer just so that nobody's confused. In the computer science literature, what physicists call fully packed hardcore dimer models are called perfect matches. So the idea is that each vertex of the graph is matched to a neighboring vertex monogamous. So in the physics way of thinking, when two vertices adjacent to each other are matched, we imagine that there's a hard rod placed on that edge with the rule that no two hard rods can touch at a vertex, and every vertex should ideally be touched by one such hard rod. That's the perfect matching problem, finding these, right? And it's very easy to see just locally that you can make this happen for regular graphs like square, triangular, grids, etc. Right? And you can also see just from some local arguments that there's an extensive entropy of these fully packed dimer covers on such regular graphs. And these are classic statements going back 70, 80 years, I think both in math, Castellan, and in physics, Michael Fisher. And there's ways of counting them using Pfaffian methods on planar graphs. But that's not what we are after, right? Because we are going to dilute the graph. So now the question is, can you do this if the graph is irregular? So let's talk of the bipartite case first. Can a diluted lattice with an even number of vertices be perfectly matched? And of course, if you want to find a perfect matching, number of A sites better equal number of B sites globally. That was the global constraint I was talking about. So let's say we have that. But it turns out that even when you put that in as a global constraint, you simply can't do it. Generically, you cannot find perfect match. What you have, the best thing you can do is what people in the computer science literature call maximum matchings, that have a minimum number of unmatched sites. And in the physics jargon, we will say that where the unmatched site is, that's the location of a monomer as opposed to a dimer, right? So you have these maximum density dimer packings that leave some vertices free. And those vertices then we will say host the monomers of that particular maximum density dimer packing. And generically, you can see that a non-zero density of vacancies, dilution, implies a non-zero density of these monomers. So a non-zero density of unmatched vertices. This is easy to see and well known. So that is the so now what we are trying to say is that these zero modes will live where the monomers live, pictorially. And the reason for saying this is that the same picture I was drawing, the same conjectured rare regions, it's very easy to see in that, there is no way you can perfectly match such a region. Again, because the boundary is all B and the number of A is bigger than the number of B, or vice versa. Have these many monomers that will live somewhere inside this region. So these many unmatched vertices must be present inside this region, no matter what you do. And it's just a local fact, right? And so there is somehow this tight local correspondence between the number of zero modes and the number of monomers in maximum density dimer pattern. That was the idea. And there's, like I said, this didn't come out of the blue. The corresponding global statement has been known for a long time. Funnily enough, in the context of trying to understand benzene-like molecules and asking if they have magnetic moments. So very chemistry, physics question. But transcribed to our language, what Longworth-Higgins showed was that the total number of monomers in any maximum matching of a bipartite graph is equal to the total number of these topologically protected zero modes in the jargon I was using. And that's a global statement about total numbers. And what we have done, in effect, is said that that global statement can be promoted to a local statement region by region. You find these regions, and inside each such region, you can construct these many linearly independent null vectors, and you have those many monomers locally. So we now know a little bit more than long way. That was the problem. So are there questions about this part? Okay, let me proceed. And we checked that this works. We went back and counted monomers in maximum density packings and compared them with the zero mode density. We found it works. But we want more. We want to somehow locate these regions, right? We are not interested in just the total number because that's what controls the physics for us. So what does this even mean in algebraic terms? Because, you're just talking about a whole bunch of degenerate eigenvectors. So we want to identify some sort of maximally localized basis for the zero energy substance. That's what we are after. And now let me make a very quick digression. There's a generalization of this problem. Again, there's some physics jargon here, which we can, I think, in the interest of time, forget. But in the end, it boils down to asking for null vectors, topologically protected null vectors, in the sense that I defined, of a random anti-symmetric adjacency matrix of a diluted graph, like the triangular net. So now ARR prime is non-zero only if R and R prime are neighbors, let's say, on a triangular grid. Now I don't need bipartite. I drop that restriction. But the price I pay is that now the hopping elements, the matrix elements, are not arbitrary complex numbers. They have to be pure imaginary. And it's still a Hermitian matrix, so it's anti-symmetric. So I have a pure imaginary anti-symmetric adjacency matrix, weighted with random weights for each edge. And I'm asking about the null vectors. And this is relevant in a different physics problem. And you can think of this both as a generalization and a specialization of the earlier case, because it's a generalization in the sense that the graph can be anything. It's a specialization in the sense that the weights have to be pure imaginary. And by an extension of the previous argument.
Sorry, I'm just a bit confused. So how do these eigenvectors differ from, just going back to quantum percolation?
Yeah.
You can imagine creating a pattern of open edges in your random environment.
Yes.
You can support an eigenvector which is compactly supported on this, right? And these occur with positive density. It's just a pattern. So and it's known that for quantum percolation, this kind of means that you have a pure point spectrum which is dense in your full spectrum. So how does that actually differ from this topologically protected?
So what I'm talking about is this special case at zero energy, right? So if you want to think of what the full spectrum is, not just the things that are pinned to zero energy. The density of states has a regular part and a singular part. The regular part is some decreasing function of epsilon coming down in energy. So there's states at, in the thermodynamic limit, there's going to be states at energies arbitrarily close to zero. So as a density, there's a density of states that comes down. But there's also this sort of delta function with weight W. And I'm focusing on the delta function. Because, that will make the most dominant contribution if I'm at half filling and at very low temperatures. At low temperatures, the states that contribute get squeezed in width, in energy width by the temperature. So as temperature goes to zero, the thing that starts dominating is the weight of the delta function at the other states you're talking about are part of the regular spectrum, and their number is going to scale with this energy window, this temperature window, right? So the other contributions go to zero with temperature. This one remains what it is. So in the low temperature limit, I'm interested in the contributions coming from this weight of the delta function, those states.
Okay, thanks.
Is this clear? I mean, I didn't fully understand this distinction between point spectrum and not, but I know that if I look at this problem, let's say this tight binding model of graphene, I get two parts to the density of states. One in the thermodynamic limit, average over samples, is a smooth function coming down to zero. And then there's a delta function at zero. There's some weight exactly at zero, which is thermodynamically significant, scales as L square. So as a density, it's a number, and that number is W. And all other states, their contribution will decrease with this energy window that is enforced by temperature. Whereas the contribution of these states doesn't go away. They're just at zero. They're pinned. So this is what dominates. So this is quantum percolation at half filling. So when the Fermi energy is pinned to zero. So you're only looking at wave modes that have energy zero in a band of temperature T around zero. So the zero temperature limit is dominated by the delta function. Is that clear?
It's not clear, but I think it answers my question.
Okay. All right. So there's a slight generalization or a specialization, as I said, that works for any graph and which is equally interesting to us. And by a similar argument, we make a connection between the monomers of a maximum density dimer packing and such modes. And again, it's a local correspondence. These so-called R-type regions are where the monomers live and where the zero modes can be constructed. The zero modes that are robust to jitter in the TRR band. So let me just skip that because this is a bit less intuitive than the bipartite case, but the general argument is the same and it's fleshed out in this paper. And this more general or more special case, whichever way you want to look at it, gels with a known result, which is again a global statement of the same type, that the total monomer number in maximum density dimer packings equals total number of such zeros. That was known. And what we've really done is just make a local statement along the same lines. So you add up all these local statements, you get the well-known globals. So this motivates me to focus on actually the random geometry of these maximum density dimer packings and ask where do the monomers live. So now let me just talk about that. So here's a triangular grid where I've diluted away most of the lattice. And what's left are these dark circles. These are the surviving sites. The dark edges are the edges between the surviving sites. So it's just a small fragment that survived. And I'm going to use this as an illustration. And I've constructed a maximum density dimer packing, a maximum matching of this, a particular maximum matching. The gray are the hard rods or dimers, or the matched vertices. The gray circles are the unmatched vertices which host my monomers. So I'm going to call them the locations of the monomers. right? So in this particular maximum density dimer packing, I've got these two monomers that live in this blue region, and I've got a perfectly matched green region, and I've got this other pink region that has one monomer. Now you can ask, starting from one maximum density dimer packing, how do I go to others? Well, there's two basic moves you have at your disposal. You can slide a monomer along an alternating path. By alternating, I mean unmatched edge, then matched edge, unmatched edge, matched edge. So you can slide it along. In effect, you move all the dimers by one to the right, and this one then goes there. So that's monomer hopping. And the other is what physicists call ring exchange. So you just rotate this picture by one. So this monomer, this dimer goes here, this dimer goes here, and this dimer goes here. Sorry. And these are the basic moves. So you can try to make these basic moves and change the maximum density dimer packing. And the point I'm making is, if you play around with this a little bit, you'll notice that the kinematics is extremely constrained. Right? You have only these two things you can do. And there's a constraint on what kind of edges participate in some of these hopping processes or ring exchange processes. Since one of these processes always ends up sliding the dimers by one or rotating by one, every edge that participates in such a process must have the property that there must be some maximum matching in which that edge is matched, right? There must be some maximum density dimer packing where there's a dimer on that. Unless that property is there, such an edge cannot be part of one of these ring exchange moves or monomer hopping moves. So that's a severe constraint. And the other thing you notice is that there are some forbidden links of the disordered lattice that can be never occupied by a dimer in any such time. So again, going back to this picture, you can play around with this if you are interested and try to move the dimers along using one of these moves wherever you like. And you'll never be able to get a maximum density dimer packing that has a dimer on this edge here, this one, connecting the blue to the blue, or on this one. So these are forbidden edges, right? And if you think about it, you immediately realize that if you just cut these forbidden links away, you've got for you these R-type monomer-carrying regions you were talking about. You were conjecturing them, but you now have a construction. All you have to do is locate where these forbidden links are and just delete them. And the graph falls apart. For example, this graph falls apart into one R region and this P region and another R region. So this is one R-type region that's guaranteed to have exactly two monomers in it and will host two null vectors of the antisymmetric weighted adjacency matrix. This one will have one monomer in it and have one eigenvector. This one will have none. So these we call the ones that are perfectly matched, we call P. So by cutting forbidden links, we can break the geometrically connected graph into further sort of break it up into these connected components, which are the R and the P type, which are connected from the point of view of the kinematics or the dynamics of these maximum density dimer packs. And now I've got to my percolation problem. Do I have 5 or 10 minutes?
You have 10 minutes.
10 minutes, good. So I'm going to skip sort of how we identify these things, because that borrows heavily from computer science. There is a theorem which in the bipartite case goes under the name of Dulmage-Mendelssohn theory, and in the non-bipartite, the general case, it's called the Galai-Edmonds theory, which basically gives you a prescription. Well, the theorem doesn't give you a prescription, but it gives you a way of classifying the vertices of any graph into 3 types. So the idea is you pick your favorite maximum density dimer packing, and you explore all these alternating paths that start from all the monomers. Just explore them and go along all these alternating paths starting from all the monomers. And if you can reach a vertex in an even number of steps, you label it even, E. If you can never reach it from one of these monomers along one of these paths, you call it unreachable, U. And if you can reach it by an odd length path, but not by an even length alternating path, you call it O. And the great result of Galai-Edmonds or Dulmage-Mendelssohn is that these labels O, U, and E, which a priori depend on your favorite maximum density dimer packing. Remember, there's a whole entropy's worth of these. In principle, these edges, the way they are, these labels, the way they are defined, depend on where I started. But the theorem says that these are properties of the graph and not properties of the maximum density dimer pack. So once you got the labels of every vertex from whichever maximum density dimer packing you happen to start with, those labels are it. Those are the labels you'll get no matter how you do it. And this is very useful because once we have this, we immediately realize that if you just delete edges between two O-type sites and edges between O and U-type sites, these are the forbidden lakes. So you just delete them. It's very easy to see that no dimer can live on edge connecting to O sites, and no dimer can live on an edge connecting O and U. So if you just cut these off, you've got a prescription. This was our basic realization. This is our answer. So if we cut these edges off, we use this Gallai-Edmonds theory to construct these labels. And having done that, we make the simple observation that we got to cut out all edges that are of this type, OO or OU. So we cut them out. And now the originally connected, geometrically connected graph breaks apart into bits. Each bit is an R-type or a P-type region, and I look at its geometry. And so this is now a constructive procedure, we claim, for looking at where the monomers live and where we can construct zero modes. And this is our key result, if you wish. And it gives us this alternate local proof of these well-known results. And just as an aside, I should say that I said that the density W of monomers or zero modes, they're the same thing we now realize, is non-zero in the thermodynamic limit. That's not always true. There are exceptions. In non-bipartite graphs, there's a class of graphs called claw-free graphs. And there are many physically relevant examples of this, which is why we got interested, where you can actually prove that any connected cluster of a side-diluted graph of this type is going to either be a single R-type region with exactly one monomer living in it, or is just going to be perfectly matched. And the fact that it can be perfectly matched if it has even parity is a very old result, which we found in the math literature. But the fact that if it's got odd parity, it's a single R-type region with exactly one monomer is new. And we were quite happy to make this connection because it tells us that on the Kagome lattice with this dilution, the density of monomers in the infinite connected cluster below the geometric percolation transition is just zero. And that has physics implications for us. So that was just an aside. But more generically, all these diluted graphs have a non-zero and smoothly varying density of monomers or zero modes. I use the terms interchangeably. Just some smooth function going to zero as the dilution goes to zero. Right? So I've just displayed some numerical experiment results for a whole bunch of us. These are the bipartite cases: honeycomb grid, square grid in 2 dimensions, cubic lattice in 3 dimensions. And these are the non-bipartite examples: stacked triangular, octahedral in 3 dimensions, and triangular and Shastri-Sutherland in 2. So these are just examples of graphs which we dilute, random site dilution, and we find a non-zero density W as we expect. And the reason we can do this is that there's well-known computer science algorithms for quickly and efficiently constructing maximum density dimer packings. And once we've got one of them, the rest of it we can. And so we can do a detailed study of the random geometry of these regions, and that's the percolation problem. So now I've got to the point where I'm talking of percolation. I kind of purposely structured it so that we have only 5 minutes for this, because now I'm just going to show you the experimental results. So in the bipartite case, we find that the area covered by these R-type regions just grows to 1 as the dilution goes to 0, which suggests thinking in terms of percolation. And when we look at this crossing probability to go from one end to the other, if it was a percolation transition, I would expect curves at different L to cross at one point, which would be the transition point. Here they don't cross. They look like they want to cross, but they don't. They cross at 0. So we try to ask whether there's a critical point at 0 dilution, and that seems to work very well as an ansatz. So we use the standard scaling ansatz, and all the data collapses. So here the conjecture is that there is a 0 dilution critical point, which is a sort of an unusual transition in itself, but not the main point of this talk. So let me move on. In 3 dimensions, we get an actual percolation transition where below this percolation threshold, which is denoted by which we identify based on where these crossing probabilities cross. This is the probability to go from one end to the other. And curves of different size cross at this point. That is our percolation point. And then this is the percolated phase. So we now have a percolation transition. Below the transition, the largest R-type region spans the lattice, and above it doesn't. Remember, the geometric transition is somewhere here, far away on the right. So it's always percolated in terms of the geometry where I'm looking. Inside the percolated phase, there's a little bit of an interesting aside here, which is that there are two infinite clusters. One are A, one are B, one of A type, one of B type. If you recall, in bipartite lattices, there can be two types of R-type regions. Either the monomers all live on A-type sites or on B-type sites. And we find that below the percolation transition, there's one of each that grows, so there's two clusters that become infinite, one A and one B, that kind of intertwine. And that's what the percolated phase looks like until a lower dilution, at which there is a second transition. At this second transition, one of the clusters, either A or B, kind of takes over from the other. And below this, you only have a single percolated cluster. So there's a kind of a spontaneous breaking of sublattice symmetry deep inside the percolated. So these are already interesting in the bipartite case. But now let me come to the punchline, which is the non-bipartite case. Here's where something fun. So here I'm showing you the probability P to go from one end of the sample to the other on a triangular grid with dilution. And the dilution is NB here. And I'm not now specifying whether I'm going from one end to the other through a R-type region or a P-type region. Whichever works, works. And I just count, can I go or not? And that probability crosses at a very well-defined sharp point. And that's a percolation transition in this geometry. Right? But when we look in the percolated phase, we notice something very funny. We notice that, for example, if you look at the mass of all the vertices that are in R-type regions, if I just plot their histogram across samples, it has two peaks, well separated and narrow. So each peak narrows with size until it's sharply defined, but these two separate peaks, very widely apart. And the reason this is happening is that the ensemble of samples, which are prepared randomly by just diluting vertices in an identical way. I prepare typically, let's say, 5,000 of these. And when I say I, of course, I mean Shauna can prepare. Right? So when you prepare these samples, you've done nothing special. But when you look at it, roughly half the samples have one, if you wish, infinite R-type region. And the other half have an infinite P-type region. So samples belonging to this peak in this histogram have an infinite R-type region, and samples belonging to this peak have an infinite P-type region. That's what we check by looking at these curves. And so this ensemble of samples is somehow spontaneously falling apart into two groups. In one group, it's the R-type regions that percolate, and in the other group, it's the P-type regions that percolate. And this is the sense in which I was saying that this weak form of this dogma that we have is violated. Because if you think about what I was saying earlier, in these R-type samples, where R-type region is percolating, there are these zero-mode wave functions that can be constructed that span the lattice. And so if you inject current or heat at one end, it can go to the other through the zero modes. But in P-type samples, there's no such zero modes. So the contribution from this delta function is missing. There can be other contributions that kind of become small as temperatures reduce, but the contribution from this delta function peak is missing. So in this sense, if you went ahead and did this thought experiment where you measured many samples and just asked what's the conductance, half of them would conduct and the other half wouldn't. That's kind of the picture. So that's why this is surprising to us. And when I say half, I mean half within errors. You can see here, I'm plotting the fraction of samples that have an infinite R-type region. Infinite in the sense that the largest region that spans the whole lattice that I have is R-type in an L by L lattice. And L ranges, from 10,000 by 10. So L, this is linear size from 10,000 to 26,000. So that's like a billion vertices. And so this is the really puzzling thing we find. And here's a picture that says the same thing. The color coding is consistent across. So here's an R-type sample. The largest region is R-type, that's brown. The second largest R-type region is purple. And these are the two P-type regions. And here's another P-type sample where the largest region is now P. The second largest P is tiny. And then there are these two finite R-type. So half the samples look like this, half look like this. So we don't know why this happens. And this is where I'd like some feedback. Now, one last thing I'd like to say is that we checked if there is a trivial reason for this. So the trivial reason might be that you look at the largest connected component of the geometry, right? The geometrically connected cluster. If it's got odd parity, you might expect it to have more monomers than when it has even parity. Going back to this special Kagome case. So we asked whether this distinction between R-type and P-type samples, the fact that you get two peaks, is somehow controlled by this trivial geometric effect. And we have done that. I won't sort of explain all the details, but we look very carefully. We set the vacancies in motion in such a way that the mass of the largest geometric cluster just fluctuates a little bit, and the number of zero modes fluctuates a little bit. And of course, the parity keeps fluctuating. The parity of the largest geometric cluster, odd or even number of sites, that keeps changing every few steps. But we find that there's no correlation between that changing and the character of the sample change. So here I'm showing time series histograms. So this P is the typical waiting time, number of steps in my dynamics, after which an R-type sample becomes a P-type sample. So, every 4 or 5 steps, it switches. This is the number of steps in my dynamics, after which odd parity geometric cluster, which is the largest cluster, changes to even parity and vice versa. That also flips every 4 or 5 steps. But if I look at the product, that also flips every, maybe 50 steps. And if you look at their joint autocorrelation, it goes to 0 just as quickly as the joint autocorrelation of the individual guys, which tells me that there is no correlation between this variable gamma, which is +1 if it's odd parity and -1 if it's even parity, and this variable sigma, which is +1 if it's R type and -1 if it's P. So gamma doesn't control. And then we have checked in 3 dimensions, we get an even more complicated phase diagram where there's these violations of self-averaging in different ways across different phases. And there are 4 different percolated phases that differ in the way things get violated. And with that, let me just stop. Thank you for waiting for the last talk. And I know I went through quite quickly at the end, but my goal was to at least give the context and the setup very cleanly and then show some results. Thank you.
Are there any questions? So I have one about the pictures you showed. Yeah, that. So it kind of reminds me of, I remember at some point you had asked me about this kind of existence of an infinite cluster not being 0, 1.
Sorry, your voice is fading. Can you speak up?
Can you hear me now?
Yeah.
I remember at some point you had asked me about existence of an infinite cluster not being a 0, 1
yes.
event.
Yes.
So here it kind of reminds me of a low temperature easing model.
Right.
Where you just flip a coin
right.
and you choose whether you're in a plus or minus state, and it doesn't violate anything about,
Exactly. So this is the point. In the icing case or in the POTS cases we are familiar with in Fortuyn-Castellan percolation, there is this symmetry, right? There's a Z2 symmetry in the icing problem, a POTS symmetry in the POTS models. And so the idea is that you run this percolation process, and after you're done, each cluster can individually be labeled by a color because there is this color symmetry. So which is why I was saying that this result that we've got somehow suggests there's some emergent version of that symmetry between monomer-carrying regions and fully packed regions. My labels R and P, remember, have to do with whether the region contains monomers, a density of monomers, or is perfectly matched in the maximum density dimer packing problem. And so there's no obvious symmetry between R-type regions and P-type regions. So this is exactly the thing I was puzzled by. So just to try to make it more concrete, what the puzzling thing is, think of the spin 1 icing model and the Fortuyn-Castellan representation of the spin 1 icing. So now you can randomly label clusters +1 or -1 in the percolated phase, right? But we don't know of a percolated phase where sometimes 0 percolates and sometimes +-1 percolates, right? +1 and -1 are related by the Z2 symmetry. And we know that there's a percolation transition below which there's an infinite cluster, and that you can label independently 1 or -2. But we don't have an example where with some probability the infinite cluster is +1 or -1, and with some other probability it's 0. And that's because there's no symmetry connecting 0 to +-1 in the spin 1 Ising model.
But isn't it the case that when you are in the discontinuous critical phase, so maybe you call it the first order phase, then you expect the 0, plus and minus
That's right.
measures to be extremal.
Yes, absolutely.
So then you would expect this, right?
That's right. But that's at the first order transition. Right. So this exactly, that's another way of saying it. I seem to have some extended region in this parameter space, which looks like it's always sitting at a first order transition. So this kind of phase coexistence, of course, we understand very well at first order transition, right? As a function of the intensive variable, there's one point at which you have a first order transition. But then at that point, you can get either this or that, and in any ratio you like, right? Depending on boundary conditions. But that happens because you went to the first order transition. So another way of saying it is I seem to have an entire extended regime where I have a first order transition. So maybe there's a different axis one has to introduce, and along that axis, this is a line of first order transition. That can happen, but we don't know such a axis, and that's why we don't know what's going on. Did I address that example correctly?
Yeah, you did. Yeah. Excellent. Okay. Thank you. So are there any other questions? If not, on the Zoom, are there any? If not, let's thank Kedar again. And
thank you. Thank you very much.